There, welcome to your lesson on exponential models. As you may have seen in the past, an exponential model is one that models exponential growth. And there's lots of examples of exponential growth in the real world. For example, here we have the human population growth chart. And we can see by year, the population is not so big, but as we get closer to modern days, the population has exploded and it grows like that, following a curve. That's exponential growth. That is what this lesson is all about. All right, let's begin here. Here we are given a model. It says the temperature T of a cup of tea is modeled by the function t of x equals 21 plus 55 times 1.9 to the power negative x. So this function models the temperature of tea, a cup of tea, where t is measured in Celsius and x is measured in minutes. So the independent input variable is time in minutes, and T is our temperature in Celsius. So basically, how much has a cup of tea cooled after it's been poured? 1 minute, 2 minutes, 3 minutes, and so on after it. A couple general questions for you to answer. How long will the tea stay warm? And I'm not asking you to use the function here, I'm just asking in general. What do you think? How long will the tea stay warm? Give an answer. Okay, number 2, will the temperature of tea ever reach 0 degrees Celsius? Okay, and can we find the temperature at different times? Because the tea's temperature changes, of course, it's cooling. Well, I hope with the last one at least, the first two were kind of like, in a way, not guessing, but using your experience in the real world. The last one, though, we can say, well, yes, we have an equation. Whenever we have an equation, we can solve things, right? So we can put in any input for time here for x, and then calculate the temperature at that time. So we can put in a time of 1 minute, 2 minutes, 3 minutes, 4 minutes after the tea was poured, and it'll tell us the temperature using this equation. It's important to look at the graph, but before we look at the graph, let's look at the equation some more. Here's the equation we were given. I rearranged some things here because there's some things we're going to look at in this lesson, and rearranging it this way is going to make them a little more clear later. So notice first I took the 21 that this started with and I wrote it at the end here. And then I took this 1.9, which has an exponent of negative x, and I rewrote it like this. The reason I did that is every time you have a negative exponent, here we have negative 1x. So I applied the negative 1 to this, and the rule of exponents says when you have something to the power negative 1 or negative 2, then you can take that thing, write it as its reciprocal, and make the power positive. So that's all I did. I dropped the 1.9 down, the negative is now gone, and that's equivalent. The reason I did that you'll see a little bit later in this lesson, why this number is important. So now let's take a look at the graph. The graph looks like this. And just a moment ago we saw the human population graph, and it was exponential growth. It was growing quickly. This one is decreasing quickly. So this is called exponential decay. It looks like this. So it shows the temperature. So look at the T starts around 50 degrees. Well, it doesn't start. It starts somewhere up here. Anyway, the T is at 50 degrees after 1 minute. It's dropping. After 3 minutes, it's around 28 degrees, and on and on. But eventually the T temperature plateaus at a certain number. What number is that? Well, I hope you notice it kind of looks like it's plateauing at around 21, and that's not coincidental. We have 21 here. So keep that in mind now. This number here tells us kind of where this graph will plateau. And in math, when a graph plateaus like that and reaches kind of a limit, an invisible wall, that wall is called an asymptote. So this asymptote is at 21, and it can be found right here. Important to know. So will the T ever reach 0? No, definitely not. It's kind of plateauing at 21, which we can say is around room temperature. So it's never going to, unless it's a cold room, it's never going to go below that temperature. How long will the tea stay warm? Well, that's up to your interpretation, depending what you define as warm. But I would say, somewhere from the beginning to 3 minutes. 3 minutes right here. I can see there it's still 28 degrees. I think that's warm enough, and after that's too cool for me. So 3 minutes of warm tea. All right, let's move on. So next thing we have for you is this. This connects to our unit. Our unit has been about geometric sequences, and we're going to connect this to that now. Geometric sequences had this rule. Notice that there is the exponent has a variable, and that's what we just said an exponential function has, a variable exponent. So here's an example of a geometric sequence. Notice it begins at 3, and then we double. We double the number. So our R value, our multiplier, is 2. Then we know by this rule we have this equation for this sequence. 3 is our first value, 2 is our multiplier, and there's our exponent. So notice it has taken on an exponential form, the variables in the exponent. What that looks like is like this. Plot those points for that sequence and you get that. Here's 3, 6, 12, 24. Connect those points and you can see that exponential growth curve. So here we have exponential growth. Now here's another sequence, geometric as well, 16, 8, 4, 2. Now the numbers are decreasing. They're being multiplied by 0.5 or a half each time. So our R value is 0.5. So using our rule, we can write 16 times 0.5 to the n minus 1. Our first value and then our multiplier. This now looks like this. The values start at 16, 8, 4, 2. They're decreasing. This is exponential decay, right? So growth and decay. Now take a close look at each of those rules or exponential functions and tell me, what is it about these rules that determines when one is increasing or growth and when one is decreasing or decay? Okay, I hope you answered that. It's the R value that tells us that. When we have a multiplier here that's greater than 1, we will have exponential growth. When we have a R value or multiplier here that's less than 1 and between 1 and 0, it's going to be exponential decay. Important rule, we'll take a look more at that. So let's investigate some things on decimals. We're going to do lots of different things. Please open up a window with decimals. The rest of this lesson is going to be very interactive. I'm going to ask you questions. You're going to go decimals and check things out. So let's get it ready now. Okay, so first thing you're going to do, graph all 5 of these in decimals. Okay, enter those 5 functions and then answer these questions. Sort them into 2 groups, the ones that are increasing and the ones that are decreasing. So which of these are rising, exponential growth, and which ones are decay? Okay, let's take a look. You should have graphed them like that. I have all 5 there. These are my growth ones, exponential growth, increasing. These are all increasing. And notice they are these 3 here. They are the ones with base 2, 1.5, and E. E, by the way, is a special number. We'll talk about it in a minute. But all of those are a certain number, and they're all increasing. And these are all numbers greater than 1. Now, let's look at the other 2. These 2 bases of this exponential graphs are both decimals between 0 and 1. They're decimal values, and notice the graphs are decreasing. So that's the first conclusion you should master from today. When you see those decimal values there as the base of the exponent, it's going to be a decreasing function or decay. All right, now for the function f of x equals e to the x, we're going to figure out what e is. What value of x gives f of x equals e? So what value of x would you plug in here to get a result of just e? Well, I hope you answered well. Obviously, we plug in 1. If we put 1 in for x, then we have e to the 1, which is just e. So now, using that idea, that when x is 1, we get an answer of e, we can look at our graph and determine what e is. So I went and I followed my graph, and I hope you did the same thing on yours. You followed your graph, you can drag along it, and then you got to where x is 1, and then it tells you what the y value is, 2.718. That is e. E is that number, and it's a very special number. We'll take a look together why in a moment. Okay, so let's recap some things. Exponential growth, exponential decay. This is a number that's greater than 1. This is a number that's between 0 and 1. Okay, so they look the same if you write them in this general form with a letter. However, in this case, a, like I said, has to be greater than 1, and in this case, a has to be between 0 and 1, and we can write it like that, and that will be decay. Okay, we just found out e is an irrational number that looks like this, 2.71828 goes on forever. That's why it's irrational. And I have another question for you. For exponential growth, what effect does a higher base value on the graph have? Okay, so if you have a bigger base number, for example here, exponential growth, if this was a 2 or compared to a 3 to 4, split that in decimals, put different bases here, 3, 4, 5, what effect does that have on the graph? Okay, I hope you answered that the higher the base value, the steeper the graph. And that's what we can see in the 3 we had here. Sorry, this is the lowest one, 1.5, and that's this one here, the least steep. The next higher base is 2, and we can see this one is here, more steep. And finally, the steepest one is the e to the x, because e is 2.718, so that's the biggest base number, and we can see it as the steepest rise. So that's the second thing you should know about exponential graphs. The base number there tells you how steep it will be, and as that number gets bigger, the steeper it is. Okay, great. We're learning all about exponential growth. Let's move on. Look at the next step in the learning process here. So here's an exponential growth graph. This is the graph for y equals 3 to the x. Now notice the graph. gets closer and closer to y equals 0 but never reaches it. What does that mean? So if you follow the graph in this direction, seems to be, like we said before, like it's plateauing at y equals 0. I put a dotted line there. It's never going to get there though. It looks like it does on here, but if you went to Desmos and followed it, it would never get to a value of 0. It would never get there. It's like an invisible wall or barrier keeping it from reaching that point. So that thing again is called an asymptote, and here the asymptote is at y equals 0. So my question to you is, in Desmos, graph y equals 3 to the x plus 2. Enter it exactly like you see it, and then describe the effect that this has on the graph of the curve and its asymptote. So describe that. All right, I hope you were able to get in there and see what happens. So let me recap what happens. This is important for you to know. Let's take a look together. So I'm going to go in here. Here is that graph we just saw. Now I'm going to change it and put plus 2 here. What happened to my curve? It was here before, and now when I put plus 2, oh, it looks like it just basically went up. The whole curve went up. So as the curve goes up, where it plateaus to also goes up. So now my asymptote, instead of being y equals 0, should be y equals 2. Look, there we go. The asymptote and the curve, they both go up together, so that where the curve plateaus moves up with the graph. Now I'm going to put plus 4, and I think we can predict where that's going to be. It's even higher. The curve moves up to plus 4, and now I should move the asymptote also up to y equals 4, because the curve will plateau there. So that number tells us all about the asymptote, and we already saw that in the t problem, didn't we? Okay, so let's go on a little bit further here. So we have a basic exponential graph here, y equals 2 to the x. The asymptote is barely visible there, but there it is. And here is y to 2x plus 4. So again, the graph has shifted up 4 units. We can see 4 units, including the asymptote, has moved up. So that's the third major thing you should know about exponential graphs. You've learned 3 key things so far. All right, so going back to our t problem, there was our equation. As you may remember, I rewrote it like this. Now it's more clear why I put the 21 at the end, because the 21 is that number that tells us how much the graph has been moved up, right? It tells us clearly how much it moved up, and we saw that in the t1 because the asymptote was at 21, just like the asymptote is at 4 here. And then I changed this number to 1 over 1.9 when I had the negative there. And that tells me 1 over 1.9, 1 divided by a number, is a decimal value. And remember, when this is a decimal value, when this base number of the exponent is less than 1, then we have exponential decay. So notice here we have exponential growth, because the base was a number greater than 1, but here the base number is less than 1, so we have decay. So all the ideas are coming together here. Really important you put the pieces together. So now let's switch from tea to coffee. Here is the function for the coffee cooling. Rewrite that in the form like we see here. And now check your work carefully. Now let's graph the coffee and tea together to compare. Here they are. Purple is tea, black is coffee. Looking at the graphs carefully, answer these questions. Number 1, which is cooling faster? Number 2, which one reaches a lower final temperature? Okay, your answers to those may have been cooling faster, but we can see the black one, which is coffee. It has a steeper slope. It's losing temperature much more quickly. However, even though it's losing temperature quicker, it plateaus at a higher temperature. So tea is cooling slower, but goes to a lower temperature eventually. We can see that. Now, third question. What point on the graph represents the initial temperature? All right, the word initial always means the beginning temperature. When would the beginning be? Would it be at 1 minute, 2 minutes, 3 minutes? No, the beginning would be at time 0. So we need to see what's happening at time 0. So I'm going to zoom in and see that part of the graph where those curves approach the axis. So here's what we see. I see coffee hit the axis at 0.88. So the initial time 0 temperature was 88. Tea, the initial temperature was 76. And then the two curves meet right here. So that means 0.4 minutes after cooling began, they had the same temperature of 63 degrees. All right, let's finish with this. All the ideas you've learned are in this one problem. Let's figure it out. Is that a general equation of an exponential graph looks like this. We have a number in front, k, then the base, a, and then the number we add at the end. So looking at all these functions fill in this table, notice in the first one we have a k value of 1 because there's a number in front here that we don't see is a 1. The value of a, the base of the exponent, 3. Then we have 0 for the c value because nothing's being added, and so on and so on. See if you can fill in the next row. And now check your work. Now try the next row. Check your work. Now check, do the rest and check your work. This is a great check on whether